Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Hello and welcome to another episode of Driven. This is an informational episode and it builds off of some prior episodes, mainly the ones that relate to mapping and how missions are created, because the next step is to consider, how does a vehicle know where it is on a map? How does an autonomous vehicle know where it's located? This episode is called AV Localization, and it's all about how autonomous vehicles figure out where they are on planet Earth or wherever it is that they're operating, most likely on planet Earth, but really just figuring out where they are on a map with respect to a mission that they may be engaged in delivering people or goods from point A to point B, or to pick up things and drop them off, what have you. So all about where a vehicle is. And one of the first things or terms that comes up is the term POSE, which stands for, well, I like to think of it as position and orientation sensor estimation. But it really just means where something is located, what its position is, what its orientation may be in some frame of reference. And typically with autonomous vehicles, we're looking at geo frames of reference or geographical frames of reference, like latitude, longitude, and maybe altitude, although that's a little bit more of a sketchy and less accurate measure of that's not necessarily reliable. But you might be looking at that with regards to traveling through multi-layer garages. You might look at it in terms of levels of a garage, or you might actually think of things in terms of altitude. If you're looking at a bridge overpass or what have you, if that's a consideration, you might consider altitude. But mainly, what's your latitude, longitude, which is your XY position with some curvatures reflected with respect to its location on Earth. And with autonomous vehicles, we found it to be particularly important to have high precision of knowledge of where a vehicle is on a map. So while your typical Google Maps or Apple Maps application may tell you roughly where you are as a human driver, if you're trying to get around in your car or trying to get from point A to point B, a rough location is good enough for you because you can pretty much look around and figure out where you're at based on that. But in a lot of cases with autonomous vehicles, you want a much more precise definition of where you are, so that you can make sure the vehicle is traveling within the lanes, the boundaries in which it's allowed to operate, to know where it's going to be traveling with much greater precision. If you're like pulling into a bus stop, you want to be able to pull in with plus or minus a few inches of accuracy, not really a few feet, and certainly not a few meters. So you have that high definition map that we talked about in a prior episode. You have a mission, which is given a destination or a series of destinations, and then the route or routes that are sort of created from that based on a map and a mission, given the destinations where you want to go, a planned sort of path or route through the map to get to where you ultimately want to be. And the key aspects of localization for a vehicle in its navigation, as I mentioned, are position, where it is, maybe what its orientation is, its roll, pitch, and yaw, or in some case, or as we like to consider it, heading. And then the derivatives of those factors. In other words, the change in position over change in time, which is speed, or the change in speed over change in time, which is acceleration, deceleration. And you might also want to know the change in orientation, a particular orientation over time, what its orientation yaw rates might be, or how fast it's sort of pitching and rolling. Those may become important factors. And one of the key aspects of localization that a lot of autonomous vehicles use, as we use as human beings in figuring out where to go these days with digital maps, is just GPS based guidance. So looking at satellites, triangulating on satellites in the sky, getting information through using a GPS receiver, telling us where that position on the vehicle, where the antenna is, might be on Earth, what its latitude and longitude may be. And with GPS-based guidance, in some cases, you're also having two antennas, dual antenna-based GPS systems that tell you where two locations on the vehicle are, not necessarily for redundancy, although you might use it for redundant reasons, but for also helping you get a really good lock on heading when you're first starting out. You can look at those two positions and figure out what your heading is when the vehicle is just sort of getting started. And then as you're traveling and navigating, you can get a more accurate heading as well from the GPS system itself, based on how the position is changing and the heading of the vehicle changes. You might be able to gather that from the GPS system, including its inertial measurement or inertial navigation units that it may have on board, magnetometers, gyros, and other things that are built into typically these integrated GPS based guidance systems to tell you what the orientation and heading and roll and pitch are of the vehicle. And of course, accelerometers telling you what your acceleration and deceleration is along multiple axes, but mainly, of course, along your longitudinal axis, so that you know that you're stopping in a sort of smooth fashion, or if you're engaged in an emergency braking situation, you're sort of controlling the braking to brake at a certain deceleration rate, but to be able to decel in time for stopping for an object in front of you. Now, that's all kind of related to obstacle detection and obstacle avoidance, which is a broader topic, but that comes as a byproduct. Some of those measurements and the use of those measurements come from a byproduct of having this GPS-based guidance system. So it's not just for localization, but it's used for other has uses in other aspects of the autonomous vehicle's operation. But one of the things that we found is with a lot of applications, having operational design domains where you're surveying where the vehicle may operate could be important if you want to characterize and sort of know in a more deterministic fashion where the vehicle's going to be operating, where it should be allowed to operate, and maybe where you don't want it to operate. So you may create this map that creates this sort of geofence or invisible fence around which, within which the vehicle you feel can safely operate. And this may be important for not just on-road applications, but off-road applications like mining applications or farming applications where you want to kind of confine the vehicle. Now, in consumer-grade automotive autonomy applications, you maybe just looking at driving all over the continental U.S. or what have you, and not be confining the vehicle, as is the case with Tesla vehicles and other vehicles that have self-driving capabilities starting to be layered into them. But in a lot of sort of production-oriented autonomous applications today, you're typically sort of or you're very often sort of looking at sort of a defined map in an area in which the vehicle can operate. So some of the other things that come from these GPS-based guidance systems, or external to them, are encoders that may be mounted to steering, or I should say, speed shafts, wheels that tell you how fast the vehicle is traveling, to also be fused into the GPS guidance system, as part of its determining its current position still, and in conjunction with GPS based information. You also have just this concept of flexible constellation selection. Um, when you think of GPS, you might think of just United States of America based satellites and constellations in the sky that we're locked onto and figuring out where we are. But there actually are a lot of other, or well, I should say a handful of other important constellations out there, that tell us, from other deployed by other countries, that you can leverage, and other sort of international organizations that you can leverage to tell the system where it is if one constellation system is particularly compromised based on where you are on Earth at any point in time, because you have to get a lock on, well, you have to get a lock on at least three for some sort of minimalist lock on position, but typically it's like 5 or 6 satellites that you need a lock on to be able to get a decent sense for where you are on Earth. Now, GPS alone will just give you accuracy. It could be up to a meter or so. That's not really great. So you typically need something beyond that to give you more precise indication for the autonomous vehicle to know where it is on Earth. And that's where RTK corrections, or real-time kinematics as it's referred to, come in. And this is a methodology by which you have your position, and then with some correction signals, you can further refine where you are on Earth based on some known fixed points, additional points that may be more local on the ground, like beacons and cell towers and what have you. And so it's really a correction service for enhancing your position accuracy. And again, you can get this down to certainly well below a foot. It might be 10 centimeters. It could be a couple centimeters of accuracy, depending on the RTK system that you're using. And there's different types of correction services available. There used to only really be these where you would set up your own towers and sort of survey where they are, and use the corrections that would come from them to know where you are in a particular location. But that's pretty limited because you have to install those towers and survey them, and it kind of confines your area of operation. But it can be really precise and more deterministic, and maybe useful still. There's also satellite-based corrections. There are services where there are additional satellites in the sky that can be used to with sort of their known position to use to give you a correction and a more accurate sense for where you are on Earth. So it's a satellite-based RTK correction service. And then kind of more popularly deployed these days are cellular-based RTK services, where you have cell towers out there in the world. And since cell phones are plentiful these days, there's a lot of cell towers, and so pretty much wherever you are in the world where there are cell towers, and there's an RTK service that you can leverage that's interconnected with those, intertwined with those, you can have cellular-based RTK corrections to tell you with tremendous accuracy. It could be, again, a couple centimeters where you are on Earth. So these are the different methods of getting where you are, and then getting a more refined picture of where you are on Earth. Now, much like you can't rely on one sensor alone, you can't just rely on LiDAR or radar, I think, for autonomous navigation and detection of where you are, detection of where things are in the world. You also have to have different algorithms, redundancy of algorithms. And in this case, for localization, I think that's important as well. Different methods, algorithms, and maybe even different sensors for figuring out where you are under different circumstances. And so in cases where you have GPS outages, you might have urban canyons, tall buildings that kind of block a GPS signal, and the vehicle doesn't quite know where it is for a few seconds. There's a methodology called dead reckoning that can come into play for some really typically pretty limited durations, for which the vehicle can project what its subsequent position and heading is based on the last known good position and heading. And it can then continue to do this by what's called dead reckoning. So you're figuring out based on your this well-known position and heading, where you are now at time t1 versus time t0, because you're looking at your wheel speed encoders. You might be looking at gyros and other sensors to tell you how you've been turning, or how the vehicle's been kind of turning left or right between those two time periods, and then over extended time periods to really estimate and project where you may be now at time t1, 2, 3, 4, 5, 6. And this works pretty well for when you're driving in a straight line and you have to dead reckon. But the more you turn and what have you, the more error accumulates with the accuracy of your position and orientation. And in general, this is something that really lasts for, it could be 10 seconds, it could be 30 seconds, maybe if you're lucky, a couple minutes of time where you can get a reasonably accurate sense for where you are for autonomous navigation. At some point, the error is going to get so big, it might get to a foot or a couple feet, and then you're way off track. You're driving off the side of the road if you're solely relying on this, and the error is just too big for it to be useful. But it can be useful for very short outages, and it is a methodology that's built into some GPS-based units and systems as an integrated solution. It's also something that, as autonomous vehicle providers, we can provide and implement as well, based on information that we have from the vehicle. But GPS and RTK and dead reckoning alone won't cut it in all situations. There's going to be cases where you have an outage for longer than you've expected, beyond what dead reckoning can handle, and that's where another technology called lane keeping can come in handy, because typically when you're driving on road, you have lanes. You have a lane line to your left or right, depending, or both sides of the vehicle. It might be a yellow line, a white line, dashed or solid, and you might have a curb on one side of you. You might have some transition from pavement to grass or pavement to gravel, and you can use cameras and in many cases LiDAR to detect these edges to the left or right of the vehicle, and detect the lines or the lanes of travel in which the vehicle should be traveling, and get some lateral position alignment. So you may sort of lose, if you lose GPS and you lose some of this other dead reckoning information, you know where you were at that last moment when you lost that information, and you can at least stay laterally positioned within the vehicle, and then maybe using wheel speed sensors and even gyros continue to really kind of dead reckon, but staying within these lane lines, and maintaining your position, basically creating a longitudinal position estimation along the way, while you have lateral position alignment within the lanes, and that can last a long time depending on the quality of the lanes, and where you are, if the lanes even exist. In some cases, uh, there are no high quality lanes, or lane definitions, or you're just in a situation where you're traveling through an intersection, and it's more open, and there's no lanes, to kind of guide you. So there's another technology called SLAM, or simultaneous localization and mapping. And this is a methodology that really, I think, had its roots in the lab, for indoor robotics applications, where you could you could sort of look at walls and look at very fixed, defined things, and triangulate, much like you do with triangulating on satellites, but triangulate on those things, saying, okay, here's a wall, here's this edge, this corner of the room over here, and here's another edge or corner of a room, and I know based on that where I am in this room. The Roombas these days are leveraging that kind of technology to get a rough sense for where they are in indoors. And again, this is something that really stems from a lot of indoor robotics applications, which would necessarily be slow moving robots in a fairly well-defined fixed environment. Now you can have furniture if you've trained, sort of your mapping solution based on objects that are going to be moving around in the environment. It's going to get messed up, right? If there was a chair that was once there that now got moved, game over, right? So you really have to use SLAM to train it on fixed known things that really aren't going to move in the environment, so the robot can sort of localize on those. And along the way, some folks who who've sort of done that sort of research, who've been sort of playing in that space, had the idea, well, hey, maybe we can apply this to autonomous vehicles as well. And it's been, again, some of this is my opinion and experience, but it's been met with limited success. It is so you're now going out into this more unstructured environment, the real world. Now, certainly there are buildings that don't move. There are certain signs and other what we call fiducials in the environment that may be relatively static, and you can triangulate on those and kind of know where you are in the world. But you're traveling at higher speeds. You're typically, obviously, with outdoor autonomous vehicle applications, you have environmental situations like rain and snow and fog and things that are going to sort of befuddle and affect the quality of using LiDAR and cameras and other sensors to detect these features in the environment. And what's more is, what we've seen is the environment changes itself. You have much less control over what's happening in the big world in which these autonomous vehicles are navigating, and in some cases, they might train the vehicle to detect trees along the way and triangulate based on these trees, but then maybe that was done in the winter, and then all of a sudden the summer comes along and there's leaves on the trees, and you're not able to triangulate as accurately anymore. I've actually seen that happen, right, with this technology. So, and it's a mapping solution that can take a long time to create, because you've got to drive all over the place, figure out all these features, and it requires a lot of it can require a lot of manual intervention to kind of look at and supervise what the software is doing to learn what are reliable features and maybe what are not so reliable features to rely upon. But suffice it to say that it can be useful in certain situations. There are certain buildings in the environment that are tall enough, and you can kind of look up and sort of gather some features from those certain signs and what have you that you might just be able to rely upon. But it's absolutely not something that you want to rely upon solely or heavily or overly. I guess I should say heavily, but it's something that can be used like everything else to augment your localization solution and provide additional guidance in the absence of other information along the way. Maybe you're now traveling in an area and the lane lines that you were using to detect where you were disappear, but there's some features in the environment that you can now leverage to keep you moving along. Now, there are other technologies out there. There's another technology called ultra wideband where you can actually mount tags on your autonomous vehicle and put anchors in the infrastructure and the environment, and it's like a localized sort of GPS system. You can with this system again triangulate on these things that may be sort of mounted in known locations in the environment. They're low cost enough so that it's not overly expensive, but it definitely can require requires augmenting the infrastructure, changing the environment, adding things to an environment like these anchors in the infrastructure, which may only require a power connection, and then they have their own sort of communication with the tags in the vehicle. But you can derive your heading and your position from use of this ultra wideband technology. Again, with some limited, your accuracy may be 10 centimeters under very, very great conditions, might get to 20, 30. And it just depends on how many anchors you have in the environment, where you're operating. But it may be useful for traveling in certain situations, like, again, multi-layer garages where you may not have lane lines, or you might not have reliable SLAM. You might not, there might some of the other AV localization methodologies that we talked about might not just be available at your disposal, and you want something more deterministic than maybe some of those other, sensor only based detection methodologies like SLAM or what have you. And this is where ultra wideband can become useful as another tool in your toolbox for AV localization. So, and that's exactly the way I would look at it. I would look at, you have these different tools at your disposal, and can bring them into a particular autonomous vehicle application based on the environment in which you're operating. There may be some environments that don't have lane lines, some that do. If it's an off-road application, you're certainly not going to have lane lines, but you may be able to detect the edges of a dirt road. But you can bring all these technologies into play in sort of a layered and redundant design architecture. And maybe you're leading with GPS and RTK as a foundation, and when you lose that, you have dead reckoning for some of the patches. You have lane keeping for longer patches and outages where the lanes are available. Simple SLAM or simultaneous localization and mapping for simple fixed features and walls, and in some circumstances, ultra wideband and other indoor beacons, or even usable in outdoor applications for more complex environments where you still want some deterministic localization, but you have outages. And so you can layer this technology, have it all, or have a subset of it, and then gracefully degrade along the way. So you may have GPS and RTK and have a good quality signal and be traveling at roadway speeds. But then if you lose some of that information, you can decide to, and you're, say, only relying on lanes, maybe you cap your speed at 25 miles per hour. If you have SLAM-based information, and depending on your confidence of it, you may travel at 10 miles an hour, you may travel at 25, depending on how confident you are in the information. Typically, you might not be traveling at some sort of high speed because, again, the knowledge that localization information is accurate is going to be subject to some verification and validation that may just not be achievable in some cases. So you may have some configurable max speeds for these different modes, lower maximum speeds based on mode confidence, depending on which mode of operation. If you're dead reckoning only at this point, or lane keeping at this point, or what have you, and then switching between the modes based on your confidence during operations. It may be that you're more confident, your confidence in lane keeping in a certain zone is greater than slam, or vice versa. And you may increase and decrease the confidence in a sort of a map basis, depending on the zones of operation which you're traveling, that you've predetermined in these more geofenced applications. In other applications, you just might not have that mapping information built in. But you can build confidence and speed cues into the maps. And of course, you can come to a complete halt if you have not enough confidence to know that your localization information is good. And then you may switch over to some teleoperation mode. The vehicle comes to a halt, a call goes back to the center, and there's someone there who's going to teleop the vehicle, move it forward to get it into the next area where a more highly confident localization methodology can kick in, and the vehicle can go back into an autonomous operation mode. So I think this layered and redundant approach to localization is pretty important, and it's going to depend on the environment in which you're operating, of course, as to what you're relying more on and what you're relying less on. But typically, I would just say and think, just to give you an idea, that GPS and RTK can provide 95%, maybe 90%, maybe 100% of the coverage that you need for certain targeted level 4 operational design domains, as you may refer to them, or areas of operation where the vehicle can rely more heavily and have a higher confidence on GPS and RTK, and leverage that and use that for its primary localization method. And then maybe there's like a very small subset for dead reckoning, maybe a larger subset for lane keeping, because there's very often lanes on the road to patch you through. Very simple slam, maybe that's a little less than, maybe it's more better than dead reckoning, but less than lane keeping. But you can leverage that to get you through where lanes might not be well defined and available. And then last but and maybe least, is ultra wideband, right? Where you might modify the environment in an area which is just completely dark from a localization perspective, and you want to sort of have a deterministic sense for where the vehicle needs to be, or may be. And then barring all that, you might fall back to teleoperation if you have no sense for where you are. So one of the things I just want to point out is, again, some pitfalls. I just really want to highlight some pitfalls of SLAM and machine learning. These are very interesting techniques. I find them personally, fascinating and interesting. But again, there's sort of research and theory, and then there's production and what works, and what you can have greater confidence in today versus maybe what hasn't been sort of created yet. And just to give you an idea, again, SLAM evolved from indoor navigation in labs and offices, but as I mentioned, it can be poorly suited for complex and changing environments. And so it's just something that you want to be cautious with. Simple SLAM, where you're relying on fairly well definable markers in the environment or fiducials in the environment, may be, you have much greater confidence in that. But an over reliance on SLAM, or just sort of leading with SLAM with any of these outdoor autonomous vehicle applications, can be fraught with peril. Machine learning also, which can be incorporated as part of SLAM and some of these other methodologies, is a very probabilistic versus a determinist approach to autonomy. And you can't really verify and validate that what the machine learned is accurate. You can test it and you can try it out. But if there's an accident or an incident, you're not going to be able to go back and sort of unpack these numbers, these numeric weights inside the neural network and figure out, oh, here's what went wrong necessarily. I mean, you're just looking at numbers and matrices and what have you. And so for production-oriented autonomy or in certain applications and environments, and over-reliance on that can be fraught with peril. But again, it can be something that you layer in with other technologies and don't exclusively rely upon it, or use it for some gracefully degraded situation, and it can get you through certain situations that you might not otherwise be able to get through. So it can be important, but again, I want to stress the sort of throw the red flags out there for an over reliance and sort of leading with such a thing. And this is sort of these two worlds of to some extent system design and certainly with autonomy development, is this sort of this probabilistic bio-inspired view of artificial intelligence versus a deterministic, more controls first approach. And there's an analogy to some extent to what happened in the early stages of flight. You saw all of these very interesting solutions where folks developed these bird-like wings, and they tried to use that to propel them and fly. And we saw, I'm sure you've seen videos of those solutions, not working out quite great in a dramatic sense in some cases. But ultimately, it was the with the Wright brothers moving forward with this sort of controls first approach, stable, keeping the vehicle, keeping the aircraft stable, and sort of not necessarily leading with the bio-inspired approach to development of flight, right? But leveraging science and things that we know can work in a more deterministic, provable, verifiable, validatable fashion is what ultimately led to the production growth of those flight, right? And so I think the similar thing may be, or could happen in the autonomy world. These bio-inspired, more probabilistic approaches that are leveraged by machine learning with SLAM are interesting. Certainly are have some demonstrable operational capability. But ultimately, is it going to be these more deterministic approaches and algorithms that one leverages, where you can prove and verify and validate that the vehicle is operating safely and reliably, that are going to enable the autonomy industry to actually blossom, much like happens with flight, right? So is that going to be what enables autonomy to take off in a production capability? Only time will tell. But it's a little thought experiment that I like to think about and wanted to share here on this episode. So just a couple summary statements with respect to AV localization. As we talked about, there's a lot of different methods to bring to the table, or at least there are a couple. What was it, 6 or 7 key methods that are sort of that can be leveraged that are used today. I'm sure there are more. In fact, I've heard of more. But in terms of the ones that are more commonly used, I think we covered here. And I would just say I think it's kind of important for these autonomous applications to very often lead with something that's the most reliable and verifiable and validatable for the environment in which it's operating, and that may be GPS with RTK, where you can get that 95% or greater to maybe to 100% coverage in an area in which you're operating. So you lead with something with the more deterministic algorithms that you could bring into the picture, such as that. Maybe ultra wideband becomes important if you're really compromised in terms of your ability with your sensors to see things in the environment. But if you can see accurately and the things in the environment are accurately seeable, like lanes, like buildings, like trees with no leaves, then other methodologies like lane keeping and SLAM and what have you can come in and provide a redundancy and a capability for the autonomous vehicle to localize and know where it is in the environment and improve overall localization. But again, it's these tools in the toolkit approach that can be important for AV localization. And we talked about some of them here today. I think in future episodes, we'd like to dive deeper into maybe each one of these and talk a little bit more about how vehicles determine where they are on Earth or where they are on a map, and what direction they're pointed, and if they're right side up or versus upside down. So hope you enjoyed this episode. We'll be diving deeper in future episodes into these topics and more. Thank you. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web, and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.